A warm welcome to everyone for a brief video presentation on the topic Optimal Binary Search Tree. Greetings to all of you. My name is Bharath. I belong to third semester of Computer Science and Engineering and Artificial Intelligence Department. The subject which I am explaining through this video is Data Structures and Applications with the course code BCS 304. The topic is Optimal Binary Search Trees. Let us look into the video. Optimal binary search trees are a crucial concept in the field of data structures and algorithms. A binary search tree is a data structure that allows for efficient searching, insertion and deletion operations. An optimal binary search tree, as the name suggests, is a BST that is structured in such a way as to minimize the total cost of searching. The total cost is typically defined as the sum of the products of the probabilities of accessing each key and the depth of each key in the tree. Optimal BSTs are essential in scenarios where frequent searches are performed on the dataset, as they provide the most efficient way to organize the keys. In this presentation, we will delve into the intricacies of optimal binary search trees, exploring the construction, characteristics, and applications. This was a brief introduction of optimal binary search trees. Now, through this video, we will look into it in more depth. Let's go on to the next slide. The next slide is on binary search trees. A binary search tree, or BST, is a fundamental data structure used for organizing and storing keys in a sorted manner. Each node in a BST has at most two children, commonly referred to as the left child and the right child. The key in a node is greater than all keys in its left subtree and less than all keys in its right subtree, making it easy to search for a key efficiently. BSTs offer quick insertion and deletion operations compared to other data structures like arrays and linked lists. They are particularly useful in applications that require frequent searching and dynamic updates. However, the efficiency of a BST heavily depends on its balance. An unbalanced BST can lead to degraded performance. Later in this presentation, we will explore how to optimize the structure of BSTs to improve search efficiency. This is about the binary search trees. Now, let us move on to the next slide about a need for an optimal binary search tree. What is the need for an optimal BST? The need for optimal binary search trees arises from the desire to minimize the cost of searching for keys in a dataset. In a typical scenario, keys are not accessed with uniform probability. Some keys are accessed more frequently than others. An optimal BST aims to organize keys in a way that reduces the overall cost of searching, taking into account the probabilities of the thing, taking into account the probabilities of accessing each key. By doing so, it improves significantly the efficiency of search operations compared to a standard binary search tree. This optimization is crucial in applications where search operations are frequent and performance is critical, such as in database systems, information retrieval, and in some of the compiler designs. This is the real need of a binary search tree. Let us go on to the next slide. Characteristics of optimal BST. Optimal binary search trees exhibit several key characteristics that distinguish them from a regular binary search tree. One of the main features is their balanced nature, which ensures that the total cost of search operation is minimized. Unlike standard BSTs, where the cost of searching depends on the depth of the node, optimal BSTs are structured to minimize the weighted sum of depths for all keys. This balance is achieved by placing frequently accessed keys closer to the root, reducing the average search time. Additionally, Optimal BSTs are characterized by their efficient use of space, as they aim to minimize both search time and memory overhead. These characteristics make them highly efficient for search-intensive applications. These are some of the main characteristics of an optimal binary search tree. Let us go on to the next slide. Dynamic programming approach. Dynamic programming approach is a technique used to solve complex problems by breaking them down into simpler subproblems. In the context of optimal binary search trees, that is BSTs, dynamic programming is employed to determine the optimal structure of the tree. The key idea behind dynamic programming for this problem is to construct an optimal BST from smaller optimal BSTs of its subtrees. The dynamic programming approach involves creating a table to store the costs of all possible subtrees of keys. By filling this table bottom up, starting from the smallest subtrees and gradually building up to the entire tree, we can determine the optimal arrangement of keys to minimize the overall search cost. This approach ensures that we consider all possible combinations and choose the one that yields the lowest total cost. Dynamic programming is instrumental in efficiently solving the optimal BST problem, providing a systematic and effective way to construct these highly efficient search trees. This is about the dynamic programming approach of the binary search trees. Let us go on to the next slide. Constructing optimal binary search tree. Constructing an optimal binary search tree involves using the dynamic programming approach to determine the optimal arrangement of keys. The process begins with defining subproblems and gradually building up to solve the main problem of constructing the entire tree. At each step, we consider all possible subtrees that can be formed using a subset of keys. For each subtree, we calculate the cost of searching in that subtree, taking into account the probabilities of accessing each key. The goal is to find the agreement of keys that minimizes the total search cost across all subtrees. By iteratively considering larger subsets of keys and calculating the optimal cost for each subtree, we can construct an optimal binary search tree. This approach ensures that the final tree is structured in a way that minimizes the overall search cost, making it highly efficient for search operations. In this way, we can construct an optimal binary search tree. Let us see a small example of constructing an optimal binary search tree. To illustrate the process of constructing an optimal binary search tree, let us consider a simple example with a set of keys and their respective probabilities of being accessed. Suppose we have keys 1, 2, 3, 4 with probabilities 0.1, 0.2, 0.3, 0.4. What happens is we start by constructing a table to store the costs of all possible subtrees. The table is filled diagonally, starting with single node subtrees and gradually expanding to larger subtrees until we reach the entire tree. At each step, we calculate the cost of each subtree by considering all possible root nodes and their respective left and right subtrees. This is an example of the way of constructing an optimal binary search tree. Let us look at the next slide. Time complexity analysis. Time complexity of constructing an optimal binary search tree using dynamic programming, where n is the number of keys. This complexity arises from the process of filling the dynamic programming table, which involves considering all possible subtrees of keys and calculating their cost. The process of filling the table involves iterating over all possible subtrees and calculating the cost for each subtree. Since there are n square subtrees in total, the overall time complexity is, despite this quadratic time complexity, constructing an optimal binary search tree Using dynamic programming is efficient for practical purposes. The number of keys in most real-world scenarios is relatively small, so the algorithm can run in a reasonable amount of time. Additionally, the benefits of having an optimal binary search tree, such as improved search efficiency, often outweigh the slightly higher time complexity of construction. This is about the time complexity analysis of the binary search trees. If this is the time complexity, let us even check what is space complexity analysis. Here, space complexity analysis of constructing an optimal binary search tree using dynamic programming where n is the number of keys. This complexity arises from the need to store the dynamic programming table, which has dimensions n plus 1 by n, to store the costs of all possible subtrees. Each cell in the table stores the cost of a subtree, which is a constant amount of space. Since there are n square cells in total, the overall space complexity is. Additionally, we need additional space to store probabilities of accessing each key, which requires O of n space. The space complexity of constructing an optimal binary search tree using dynamic programming is where n is the number of keys. The complexity arises from the need to store the dynamic programming table, which has dimensions n plus 1 by n, to store the cost of all possible subtrees. What are the advantages of optimal binary search trees? Optimal binary search trees offer several advantages over other search tree implementations. One of the main advantages is their efficiency in terms of search operations. By organizing keys in a way that minimizes the total search cost, optimal BSTs ensure that search operations are performed as quickly as possible. This is particularly beneficial in applications where frequent searches are conducted, such as database systems and information retrieval. Another advantage of optimal BST is their ability to reduce the overall cost of search operations. By placing frequently accessed keys closer to the root of the tree, optimal BSTs minimize the average search time, leading to faster and more efficient searches. This is the main advantage of optimal binary search trees. Now let us see what are the disadvantages of optimal binary search trees. Despite their advantages, see, wherever there is an advantage, there has to be certain disadvantage. Optimal binary search trees also have some disadvantages that should be considered. One of the main drawbacks is the complexity of constructing an optimal binary search tree. The dynamic programming approach used to construct an optimal BST has a time complexity of O, where n is the number of keys. This means that for large data sets, the construction process can be computationally expensive. Another disadvantage of optimal binary search trees is their sensitivity to changes in the input distribution. If the probabilities of accessing keys change frequently, the optimal arrangement of keys in the tree may be recalculated, leading to additional computational overhead. These are some of the main disadvantages of optimal binary search trees. Let us move on to the next slide. What are the applications of optimal binary search trees? And optimal binary search trees find application in various fields where efficient search operations are crucial. One of the primary applications is in information retrieval system where large data sets need to be searched quickly and efficiently. By organizing keys in a way that minimizes search cost, optimal BSTs can significantly improve the performance of these systems. Another important application is in database indexing, where optimal BSTs are used to organize the keys in a database table. This allows for a quick retrieval of data based on a specified key, which is essential for maintaining the efficiency of database operations. Optimal binary search trees find applications in various fields where efficient search operations are crucial. One of the primary applications is an information retrieval system where large data sets need to be searched quickly and efficiently. By organizing keys in a way that minimizes search cost, optimal BSTs can significantly improve the performance of these systems. Another important application is in database indexing, where optimal BSTs are used to organize the keys in a database table. This allows for quick retrieval of data based on a specific key, which is essential for maintaining the efficiency of database operations. This is the application of binary search tree. Let us compare binary search trees. Optimal BSTs are often compared with the other type of search trees, such as AVL trees, red-black trees. One of the main differences between optimal BSTs and these other trees is the construction method. While optimal BSTs use dynamic programming to construct the tree based on key probabilities, AVL trees and red-black trees rely on balancing techniques to ensure that the tree remains balanced. In terms of search efficiency, optimal BSTs generally outperform AVL trees and red-black trees, especially when the keys are not uniformly distributed. This is because optimal BSTs are optimized for the specific probabilities of accessing each key, leading to a lower overall search cost. This is how we can compare the optimal binary search trees uh, with the other kinds of search trees which are possible. Now, before we end it, let us look at a conclusion and summary. In conclusion, optimal binary search trees are a powerful data structure that offers significant advantages in terms of search efficiency by organizing keys in a way that minimizes search cost. Optimal BSTs can improve the performance of search operations in various applications, including information retrieval, database indexing, and compiler design. Despite their advantages, optimal BSTs also have some drawbacks, such as their sensitivity to changes in the input distribution and their high space complexity. However, for many applications, the benefits of using optimal BSTs outweigh these drawbacks, making them a um, valuable tool in the field of data structures and algorithms. Overall, optimal BSTs are an important topic in computer science, and understanding their construction and application can greatly enhance one's ability to design efficient search algorithms. Thank you everyone for being a part of this video. See you soon in the next video. Thank you very much.